So what we're going to think about now is the following, which is going to be a sequential game. So when we were looking at the prisoner's dilemma game, a big part of the problem was that both players could not see what the other person was doing, right? So if instead we had a situation that looked like player one got to choose an action, player two got to choose subsequent to that, then potentially we might have a different outcome, right? And so we're going to think about sequential games. We're going to think about how the sequencing is going to impact the outcomes that will be played, right? And there are going to be two things that we're going to do. So the first thing that we're going to look at is a game similar to the game that we looked at previously, where player one gets to choose whether or not to like player two's photos, and then player two, after having observed what player one did, gets to choose. So we're going to think about what are some of the equilibria of those games. Then the second application we're going to look at is we're going to go back to the context of firms, where we have firms that have the opportunity to choose quantity. So in the Cornell case, both firms are choosing quantities simultaneously. But what if instead we had a market leader, where one firm got to act first, and then a second firm got to act after that, after the leader? Like, is there some advantage to having these sorts of differences in the timing? So we're going to explore that. And you may ask, well, okay, we're looking a lot at producers and consumers. What does this have to do with education, right? So today I'll hand out to you a theoretical exercise where what you will do is look at college admissions. And this is something that I study. So in this context, you can think about each school as being a firm, and each school is choosing like how big it's going to be, right? And if a school becomes larger, potentially the school can earn more profits, right? Because that school is going to have more students, it can charge them tuition, and it can bring in more revenue. But on the other hand, if everybody can go to your school, then the school is no longer selective, right? And so the school becomes less prestigious, and perhaps the school itself cares about that selectivity. And so there's going to be this trade-off, right? Like having a really small school is really good because you get to, oh, I go to Clemson, you know, like only 33% of people are able to get into Clemson, so that means that like it's very selective, not a big shot, right? But at the same time too, the university might want to make profit. So it's this trade-off. Students will want to come if you're selective, but if you're too selective, you won't have enough students coming so that you make profit. And so this is going to be the relevant trade-off that we're going to see there too. And just one other big picture point too. I know at this point you might be saying like, why do we need all of these techniques? Why do we need all of these tools, etc.? It gives you so much mobility in terms of your ability to be able to think about a situation, to model it, to map it onto an economic model, to solve it very generally, to say, well, if the parameters were this is what the answer would be. If the parameters were that, this is what the answer would be too. Because we're always trying to understand the world as it is, but we're also trying to think about, well, what if the world were different? If the world were different, if these parameters were different, would we have a different outcome as well? Okay. So let's look at the following sequential game. So we're going to have Jim and Sally, and I'm going to draw this decision tree, this game tree. So Jim is going to get to move first. And Jim can choose to like or not like Sally's pictures, right? So this is going to be time 1. This is going to be time 2. Sally is going to get to move here. So Jim chooses to like or not like Sally's pictures, and then Sally is going to get to choose to like or not like Jim's pictures. Okay. So if they both like each other's pictures, Jim is going to get 8 and Sally is going to get 8. So this is Jim's utility. This is Sally. However, if Jim chooses to like Sally's picture, but Sally chooses not to like Jim's picture, Jim is going to get -1 and Sally's going to get 10. If, on the other hand, Jim chooses to not like Sally's picture, Sally chooses to like his picture, we're going to get 10 minus 1. And if we have Jim choosing not to like Sally's picture, Sally chooses not to like his picture, we're going to get 0, 0. Right? So to solve these sequential games where we have complete information, so in the sense that everyone knows what the payoffs of each other is, and they also know like who is playing when. What is going to happen is we're going to use a solution concept where we're going to solve this game backwards, right? And so we're going to say, what's the optimal decision for Sally to make if Jim were to like her picture, or if Jim were to like her picture? If Jim were to like Sally's picture, Sally would be in this game here. She would be choosing between whether to like him or not like, whether to like his pictures or not like his pictures. If instead Jim chose not to like, Sally would be playing this sub-game here, right? And so that's the way to think about it, right? Like each of these steps here is going to be a sub-game. And what we're going to require is that in each sub-game, an individual is playing a Nash equilibrium, or they're best responding. Any questions so far? All right. So let's look at this sub-game here. If we're in this scenario where Jim has chosen not to like Sally's picture, Sally now gets to choose whether to like his picture or not like his picture. What is Sally going to choose? And why is she going to choose not to like his picture? Right. So if Sally chooses not to like his picture, she's going to get a bump in utility of 10, right? If she chooses to like his picture, she's going to get 8. Everyone sees that? So she's going to choose not to like. What if we were in this world here where Sally was choosing between whether to like or not like his picture, given that Jim did not like her picture? What is Sally going to choose here as well? She's going to choose not to like, because if she likes his picture, she gets -1. If she chooses not to like, she's going to get 0, right?
Quick question. Where is the distinction between this being sequential and the prior game being simultaneous?
Where's the difference? Where's the distinction between this game? Okay, so in this game here, these are going to be sub games, right? These are going the sequencing is going to come through the fact that Jim is going to be able to observe what Sally does, and Sally is going to be Jim makes a decision.
Sally responds to that decision.
That's right.
How is that different than the way we were explaining the prior game? I guess that's my question.
Oh, how is this different from the way? So in that game, both players are going to be moving sequentially. They're going to be moving simultaneously.
So like it on day 1, we do it at the same time.
Yeah. So you can think about, so perhaps the analogy of liking versus not liking for the first game was not a good one, because like typically we think about that as being a simultaneous game. So you can think about that as, you can think about the first game as being more like, I put you and Andrew in 2 separate groups. Like kind of like a law and order asking you, I'm trying to see which one's going to confess first. Right. Okay. Now, so this is going to mean that if we're in this scenario here, that if Jim were to like Sally's picture, he knows that she is going to not like his picture. So Jim is going to be choosing his utility. If he goes to this node, he knows for sure it's going to be minus 110. This is going to be the payout matrix. And if we're at this node here, it's going to be 0, 0. Right? And so now Jim is going to know, if I choose like, we're going to get to this part of the payout matrix here, where I know for sure Sally's going to choose not to like. If I choose not like, Sally's also going to choose not to like. And so now Jim gets to choose between, does he say like or does he choose not like? And what is Jim going to choose? Because Jim is going to get 0 as opposed to -1. And so this game is going to be solved by what's called backward induction. So we go to the end of the game and then we're going to work our way forward. And in that way, it's going to be different from the simultaneous work game. Now, any questions on this? Okay. So what we're going to do is, the reason why I put this up here is because I want to take this to the context of 2 firms where they're going to be acting. And I think there it's going to be even more clear. So in this context, there's going to be a market leader and there's going to be a market follower. So let's say, for example, that Clemson made its admissions decisions first. Clemson decided who it was going to take versus who was not going to take, and then USC decided after Clemson, right? There's the potential that there could be this first mover advantage. And what we want to do is we want to see, do we capture that in this type of game theoretic model? So, the firm that moves first is going to be called the Stackelberg leader. So in this context, we're going to have 2 firms.
I have a question real quick.
Yes.
Back to the sequential games.
Yeah, sure. Yeah.
So Jim, with Sally gets to make a decision after Jim does, but Jim kind of has the intuition of what she is gonna do based on his decisions, so he chooses accordingly?
Exactly. So it's
Okay.
kind of like Jim is saying, okay, I know that Sally's going to choose after me, but given the options that Sally's going to face, what do I think she's best? What do I think she is going to do? And then I take her best response and then I put that into my optimal decision.
Gotcha.
Right? So maybe this is a better way to say it. So like, and we're going to see this very clearly here. So like in the case of two firms, what's going to happen is firm number one that gets to move first is actually going to be maximizing its profit given the best response of firm number two, as opposed to we find the best response functions and just finding where they intersect. So it's like I get to observe your actions, and so I'm going to be able to like optimize over your like observed actions. Or or a better way to think about this is that I'm going to get to constrain what you're able to do. Right? So let me set up this problem and then I will explain it in more detail. Okay. So we're going to consider two firms, and they're going to face some inverse demand, P of capital Q, where capital Q is just going to be Q1 times Q2. And this is going to be exactly identical to the Cornell case, where this was a simultaneous move game. This is the inverse demand, so it's going to depend on the total quantity. The marginal cost is going to be 10 for both firms. And what we're going to say is that firm number one moves first. So the way that we're going to solve this game is by backward induction. So firm number one is going to say, what's going to be the best response of firm number two? And then we're going to take firm number two's best response and put that into firm one's profit function. And then firm one is going to optimize its profit given firm two's best response. This is going to be different from what we did in the case of the Cornell competition, because in the case of the Cornell competition, we solved for the best response functions of each firms and then we set them equal to each other simultaneously. But what the leader is going to get to do is the leader is going to get to optimize its profit over the best response of the other firm. Does that make sense? Any questions on that? Okay. Firm number two. Wait a second. Okay. So what's going to be the profit function for firm number two? Who can tell me what the profit function for firm number two is? Arturo, you're going to come right on board?
We don't know. I mean, I can help. I don't know.
All right, let's do it. Okay, so profit has two components. What's the first part of profit?
Revenue
Revenue. Okay, so revenue is what?
is asset.
No. What is revenue? What's the definition of revenue?
Oh, it's whatever you get.
Right, which is what? So if I know the price and the quantity, how do I get the revenue?
Like structure.
No. What's revenue is price times quantity, right?
Yeah.
Okay. So what's the price?
What is 100?
What's the price? This whole thing here is the price. So let's write that. So 100 minus 5 Q1 plus Q2, that's going to be the price, right? And what's the quantity the firm 2 is going to produce? Q2, right? So you multiply this whole thing by Q2. Yeah. And then you have to put a bracket around this whole thing here. Around here. And then we subtract the cost, right? What's the cost for each unit? 10, right? So it'd be minus 10 times what? Right, so how many units is firm 2 going to produce? No, firm 2 is going to produce Q2 units, right? So it's minus 10 times Q2. Yep. Okay. So we're gonna, so the profits for firm 2 is gonna be 10 minus 5 times 5 times Q1 plus Q2 times Q2 minus that, right? And then we showed from the previous class that the best response function is just going to be, to find the best response function, we take the derivative of the profit of firm 2 with respect to quantity 2, right? And when we do this, we just get 100 because we have 100 times Q2, right? Minus 5 times Q1, Q2 derivative with respect to Q2 is just going to give us minus 5 Q1, right? And then we have minus 5 Q2 squared, which is just going to give us minus 10 Q2, right? And then we have this minus 10 Q2, which is just going to give us minus 10. Right? Everyone following this?
Yeah.
What's,
Can you like hold up a second so I can write that down?
what's the delta pi
This is
two?
pi, yes, pi.
What's that?
This is the partial derivative of the profit of firm 2 with respect to Q2.
Just Q2 file?
Yeah. Exactly. And we set this equal to 0. Does everyone see this? This is exactly what we had from the previous class. Now, to get the best response, we want Q2 as a function of Q1. So Q2 is going to be equal to, let me write this out more simply. So we get 100 minus 10 is just going to give us, so we get 90 minus 5 Q1 minus 10 Q2 is equal to 0, right? And the best response of firm 2 is going to be, given a quantity that firm 1 produces, what's the optimal quantity for firm 2 to produce? So we need to solve this equation for Q2 as a function of Q1, right? So we solve, let's call it CR for Q2. We get that 10 Q2 is equal to 90 minus 5 Q1. So Q2 as a function of Q1 is just going to be 9 minus a half Q1. Does everybody see this? Any questions on this? Okay. Now, firm number 1 will maximize profits given the best response of firm 2. So what that means is that when we write down firm 2's or firm 1's profit, we're going to actually plug in the best response directly into firm 1's profit function, which is very different from solving for the best response for firm 1 first and then equating that to the best response for firm 2. Does everybody understand that distinction?
Can you explain how you get from 10 Q2 to the next one?
Yes, so this is, I divide through each side by 10, so you get 90, so you get 10 Q2 divided by 10 is Q2, 90 divided by 10 is 9, and then 5 divided by 10 is a half.
So it's Q2 is a function of Q2.
Oh, this should be Q1. That was labeling here. Sorry about that. Very nice catch. Any question? Okay. All right. So the profit for firm 1 is going to be,
Dr. Blair,
Go
sorry,
ahead.
is this supposed to be BR?
Yes.
It just, it just kind of looks like B2, so I was just making sure.
Oh, yeah, where is that?
In the sentence right now.
Yeah. Oh, given the best response of firm 2. Thank you very much. Okay. So the profit function for firm 1 is just going to be the price, which is 100 minus 5 times Q1 plus Q2, times the quantity that firm 1 produces, which is going to be Q1, minus the cost, which is going to be 10 times Q1. Now, what we did with the Cournot case is we solved for the best response function for firm 1, and then we made them best respond to each other, right? But in this case, what we're gonna do is we're just gonna plug the best response function for firm 2 directly into the profit function for firm 1. Because firm 1 is gonna be maximizing its profits given that it knows the best response of firm 2. And so this is how the sequential component of the game is gonna enter. Does that make sense? So in the Corno case, we solved for the best response of firm number 1. And then solved for the Nash equilibrium. But in the Stackelberg case, we insert the batch response function for firm number 2 into firm number 1's profit function. And then we maximize firm number 1's profit. Is everybody clear on how this is different from what we did in the past?
I have a question.
Please.
I was sort of catching up writing. How did you get the profit function of Q1? What did you plug that into?
The profit function for firm 1?
Yeah.
Okay, so this is going to be the price,
Okay.
the market price times the quantity that firm 1 produces minus the marginal cost for each unit times the quantity that firm 1 produces. So
Okay.
this is just the definition.
Okay,
So
okay.
we haven't substituted anything in that.
Okay, gotcha.
Okay. So now, so we substitute, I spelled this wrong. The batch response of firm number 2 into the profit for firm number 1. What we will get is the profit for firm number 1 is going to be 100 minus 5 times Q1. And then we have to put in the best response for firm 2 here, which is going to be plus 9 minus a half Q1 times Q1 minus 10 Q1. Let me stop there and ask if there are any questions. This here is just the batch response function for number 2. Does that make sense? Okay. All right. Everybody with me up until this point? Are there any questions before I move on? So in the Cornell case, we solve for the 2 batch response functions, and then we solve for that equilibrium. Here we solve for the batch response function of the firm that moves last, and then we put that into the profit function for the first firm, and then we optimize over that. Any questions? Okay, good. All right. So now let's do this. We take the derivative of the profits of firm 1 with respect to Q1 and set that equal to 0. And what that's going to give us is we have 100 times Q1, so that's just going to give us 100. Then we get minus, we can add these 2 together, right? So we're going to get, this is just going to be a half Q1 because we have Q1 minus a half Q1. So we have 5 over 2 Q1 squared, right? Because we have 5 over 2 Q1 times Q1. When we take the derivative of that, that's just going to give us minus 5 Q1. Everyone sees that? And we also have minus 5 times 9 times Q1, which is minus 45. So then that's just going to give us minus 45 when we take the derivative. And then we also have this minus 10 Q1 here, which is just going to give us minus 10, and that's going to be equal to 0. Does everybody see that? So that's going to imply that 5q1 is equal to 100 minus 35 minus 10 is just going to give us 45. Right? And so q1 is going to be equal to 45 over 5, which is equal to 9. Did everybody follow the steps that we used to get here? Who did not follow the steps that we used to get here? Don't be shy if you did. I can explain them. Any questions? Who understands? Raise your hand if you understand. If you don't, raise your hand. Okay, great. So this is Q1. How do we find Q2 star? Yeah, we just plug it back into this best response function here. So Q2 star is just going to be 9 minus a half times 9, which is going to be 9 minus 9 over 2, which is just 9 over 2, or 4.5. Right? We only have 1 minute remaining, so what I want you to do is, so from the Cornell case, we had Q1 star equals Q2 star equals 6, but from the Stackelberg case, we have Q1 star equal to 9 and Q2 star equal to 4.5. So in this case, firm number 1 is going to produce more than firm number 2, right? But we can also show, so what I want you to do is just check that the profits for firm 1 is greater than the profits for firm 2. Just do that on your own and check that. Any questions?
Yeah, on the bottom,
Yeah.
the Q star 2, maybe like make a difference between the Q's and the 9s.
Thank you. Any questions on this? Okay. So that's what we have for today's lecture. Please bring your homeworks and you can turn them in to me. And then on your way out as well, like collect a copy of the next homework theoretical exercise. And I'll send them an email. Email me if you have any questions about this. Yeah, when that is in a week's time.
We submitted the homework on Canvas, is that right?
Say that again?
We submitted it on Canvas and submitted the file?
Oh, you did? Okay.
Yeah,
Can you also send an email to Shannon?
Sure.
Yeah. You can just bring the homework right here.
Don't worry about that. I'll figure it out.